Mic check. Good morning, good evening, good afternoon. This is Dr. Garais, and this is BIO111. And this is the slower, more meticulous version of your Chapter 9 lecture. Currently, my Unit 3 lectures that are on announcements, they're quick. They're assuming that you've already went through the material. But I'm about to go over the material as if we had a lecture today. Today is Wednesday, November 22nd, right before, what do you call that? What is tomorrow called? It's called Thanksgiving. So you can fast forward this part. Trying to get access. I don't understand. This is my laptop. But you could skip this. Okay, need verification. Okay. Now, just as also a little announcement, I also added some stuff for BIO111 lab. Since we missed a lab this week, I put a video. Start looking at your muscles, of course, assuming that you've already done your quiz 4, which is up and running. And probably by 12 noon today, your laboratory midterm examination should be up and running. So look at that in Bio 111L for laboratory. So go over modules, and now we are well into Unit 3 lectures. And we're now going to go look at Chapter 9. Next week's Exam 3 will be on Chapter 7, 8, and 9. And next week, prepare to be there all day, like 8 to 1, because we have 4 chapters to do and a lot of preparation for week 5, which is, final assessments. Okay. Why is it taking forever to load? Okay, here we go. And while I'm here, might as well also talk about what looks good for Chapter 9, muscle. Now, the first slide, of course, it's important because this has been asked on the tissues, quizzes, and exams. Skeletal cardiac muscle. Know which one is voluntary, which is skeletal muscle, and of course, they're attached to bones. They're consciously controlled. Now, remember, add rhythmic to cardiac and smooth muscle. They are rhythmic and they're also not consciously controlled. Okay. Syncytium, add that to the cardiac muscle because remember, due to the cap junctions, they talk to each other directly. Cardiac muscle, or the cardiocytes. Smooth muscle, also known as visceral muscle, add that to your notes as well. All the stuff that we went over before, you can apply it and add it to this, and you kind of already should know the 3 types of muscles and their characteristics. Definitely alpha question, must know. Skeletal muscles, attached to bone, voluntary, yada, 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 right? It's stuff that we already know. What don't we know yet? Okay. This, you can see, they're bolded, they're bulleted. It's important. And if you're looking at it by words, fascia is the overall covering. Know the difference between tendon and ligaments. We already know from the connective tissue lecture that ligaments connect bone to bone, tendon connects muscle to bone. And the aponeuroses covers the tendon, okay? You'll also have connective tissue that bundles up the muscles in its different layers. And you're going to see something similar to this when you are looking at nerve cells as well. We already kind of saw it in bone, how the osteons get bundled up to form functional units of bone. Well, here is a picture of a functional unit of muscle. So this slide 4, and slide 6, they should be put on top of each other. So these are the words versions, and this is the picture. And you know I love pictures. So when we're looking at this, we're looking at the tendon. The tendon is part of the muscular fascia. Fascia is the covering of the entire muscle. And if you look at the tendon here, it's connecting the muscle to the skeleton, hence the term skeletal muscle. You then see there's, in order to make a muscle, you got a whole bunch of fascicles, which are these structures here. So you got to think of it like a large rope. If you've ever seen a large rope is essentially made out of a whole bunch of threads that were braided together. Those threads got braided together to make small, string. The string then got braided together and held together, and then, makes the larger rope. So the muscle itself, right? The whole entire muscle, the big overall covering is the muscular fascia. But then right underneath that, let's see if we can get a real good close-up on this. If you see all these fascicles, they're covered by, overall, they're all bundled together with the epimysium. Okay? So the epimysium covers a whole bunch of fascicles. And the perimysium covers the fascicle itself. Okay? So if we're looking at layers, muscular fascia, which is connected to the tendon, then it has the epimysium, and then goes the perimysium is now covering all the fascicles. You will also see that muscles are chock full of arteries, veins, and nerves because we have to control these muscles. They're voluntary. And remember, that is your descending, also known as your efferent fibers in your homeostasis arc. Now, we have the fascicle here, arteries, veins, and nerves. And then the fascicle is the next layer of organization. Here is a whole bunch of myofibrils that were all bundled together. They get all bundled together, and they get all covered together with the endomysium. So the endomysium is now covering a muscle fiber. So this next level of organization is muscle fiber. So fascicle gets covered by the perimysium. The muscle fiber itself gets covered by the endomysium. Okay. You also have the sarcoplasmic reticulum here. We recall in previous lectures that calcium is one of the main ions that turn things on. Your sarcoplasmic reticulum has a whole bunch of calcium in it. Because what's the greatest place to have an ion that turns things on? Right there, right on top of your muscle fiber. Muscle fibers are composed of myofibrils, and we're going to talk more about that structure. Then myofibrils are composed of filaments. So the smallest anatomic structure on this diagram for the muscle, skeletal muscle in specifically, is a filament. Myofibrils, they get surrounded by the sarcoplasmic reticulum, and then muscle fibers get surrounded by the endomysium, fascicle gets surrounded by the perimysium, and all of this gets surrounded or bound by your epimysium. The next layer is the muscular fascia. That is the most superficial, tough layer, and it's tough, T for tough, connected to tendon, connecting to something even tougher, which is bone. So this slide, very important. It's related to slide number 4. Very important, right? Know these terms and know what they are. Here's some tendons, aponeurosis, just a nice sample on chapter 5. Now, muscle fibers are multinucleated. You have sarcolemma, which is covering of the muscle fiber. Sarcoplasm, that's the cytoplasm of a muscle fiber. Now, you have your sarcoplasmic reticulum. It is the endoplasmic reticulum of muscle. And what's really important, we've already talked, there's calcium. Now, we know that the nerve impulses that turn on a muscle or make a muscle contract, because that's the main characteristic or skill set of muscle. Its only function is to contract. It needs calcium to turn it on, to contract, and it also has these transverse or T tubules that will relay that electrical impulse to the sarcoplasmic reticulum. Once that electric impulse hits that sarcoplasmic reticulum, the sarcoplasmic reticulum, which was this thing right here, will then release calcium. Here's a deeper view and of this picture here. They're looking at the level of the myofibril, which is here. All right, and you can see the T tubules. They're here, transverse tubules. They'll connect the different sarcolemma to the nervous system, because that's very important, because the nerve has to send the electrical signal to let go of the calcium so that the muscle can contract. You have this I band, A band, H zone. Yeah, I wouldn't look at this too deeply. This is just a we're going to have a better explanation of this momentarily, right? So you don't need to know what an I band, A band, H zone. Don't need to know that. But what you do need to know is that these things, the myofibrils, are formed up of 2 sets of filaments. Now, remember the overall function of a muscle, it's to contract. These 2 filaments attach to each other and then pull upon each other, and then it shortens or contracts the muscle. It's you're made out of thick filaments, which are called myosin, right? And thin filaments, which are called actin. These are all made out of proteins. And this is how I remember actin, actin, right? Now this head cross-bridging, troponin, tropomyosin, right? Let's look at it when we're looking at this. So this is a very static, hard to look at thing. So I'm going to look at YouTube. And I think the Khan Academy one was pretty good. Just do muscle contraction. Yeah, this one I used before. So let's look at this. And
you can feel it. The dream becomes a pursuit. And with vitiligo, the pursuit for your...
And I'll pause it and talk about it as we
Muscle
go along.
contraction is at the basis of all skeletal movements. Skeletal muscles are composed of muscle fibers, which in turn are made of repetitive functional units called sarcomeres. Each sarcomere contains many parallel overlapping thin, actin, and thick myosin filaments. The muscle contracts when these filaments slide past each other, resulting in a shortening of the sarcomere and thus the muscle. This is known as the sliding filament theory. Cross-bridge cycling forms the molecular basis for this sliding movement. Muscle contraction is initiated when muscle fibers are stimulated by a nerve impulse and calcium ions are released. The troponin units on the actin myofilaments are bound by calcium ions. The binding displaces tropomyosin along the myofilaments, which in turn exposes the myosin binding sites. At this stage, the head of each myosin unit is bound to an ADP and a phosphate molecule remaining from the previous muscular contraction. The myosin heads release these phosphates and bind to the actin myofilaments via the newly exposed myosin binding sites. The two myofilaments glide past one another, propelled by a head-first movement of the myosin units, powered by the chemical energy stored in their heads.
And this is called the power stroke. When the myosin heads utilize ATP and use up one of the high energy phosphate bonds, it pulls on this. And then when it pulls on it, it shortens the filament. You shorten a whole bunch of filaments, you're going to shorten the overall length of the muscle, hence contraction.
As the units move, they release the ADP molecules bound to their heads. The gliding motion is halted when ATP molecules bind to the myosin heads, thus severing the bonds between myosin and actin. The ATP molecules are now decomposed into ADP and phosphate, with the energy released by this reaction stored in the myosin heads, ready to...
Now, did you notice that there was an ATP ACE? So ATP ACE is an enzyme. It breaks down the ATP so that we can get at the high energy phosphate bond.
Used in the next cycle of movement. The myosin heads resume their starting positions along the actin myofilament and can now begin a new sequence of actin binding. The presence of further calcium ions will trigger a new cycle.
And this is the sliding filament theory. You have the actin, and the myosin, right? Think of it like all of this starts moving towards each other, and it'll shrink everything. And once it shrinks everything, that means you have contraction of the muscle. All right, and that's Alila Medical Media muscle contraction cross bridge cycle animation. You could look it up on YouTube. I always use this video. Now, what does that mean to us? That's my PowerPoint. So how can I ask and how can we look at these questions? First of all, you got to know what's the thin filament, what's the thick filament. Of course, actin, thin filament, myosin, thick filament. The myosin thick filament has the myosin heads. That's what attaches to the actin. And what you now know the two major things that are required for muscle contraction, which is ATP and calcium. We get the calcium from the sarcoplasmic reticulum that surrounds the muscle fibers, and then of course you get the ATP from mitochondria that surrounds everything, and we already know that process. So when we look at, we can look at this, composed of myosin protein, and that has the thick filaments, has the heads. Those heads, that's where ATP gets attached to it. Once ATP gets attached to it, ATPase breaks it down. ATPase then breaks down the phosphate bond, and then you have release of energy, and that's the power stroke. Now, the thin filaments, they mentioned troponin and tropomyosin. If we're looking at this, troponin and tropomyosin, they're like this, all this purple stuff. Because the only time troponin and tropomyosin get opened up so that the myosin heads can attach to it is when there's presence of calcium. So as long as there's calcium present, right, the muscle can contract. And we're going to learn a little bit later that that doesn't happen forever. You can't contract muscle forever. You have to eventually rest and recharge. Okay, here's a classic example. Pick up something that's relatively light. Hold it out in your arms, like at arm's length, and hold it out in front of you. See how long you can do that. You won't be able to do it forever because there's only so much calcium, there's so much ATP, and it has to be recycled. And we already now know it has to come from a signal from a nerve. That nerve is designated as a motor neuron. We know that descending fibers or efferent nervous system or nervous fibers are also motor fibers. So those connect to skeletal muscle. Now, this is a nerve. The nerve has insulation, it's in the form of fat, and then it has nerve endings. This is a motor nerve. Motor nerves attach specifically to skeletal muscles. They are part of the efferent nervous system or the efferent pathway, and they are voluntary. You have to think about doing something, and then it goes downward or efferently to the muscle. Now, this thing right here, this is the basis of pharmacology, a lot of things in pharmacology. You'll also notice that all of this requires a ton of energy. These are all mitochondria. So at the end of a nerve, which has an electricity, and that electricity is called an action potential. We call it an action potential because it's a signal. There's a potential for the muscle to do some work. Now, how does it do it? Electricity, and called the action potential, comes down this nerve. Once it gets into the motor end plate, it ends up in the space called the synapse. The electricity then sparks the mitochondria and to make energy so they can package all these vesicles. These vesicles contain neurotransmitter. And for skeletal muscle, the only and main neurotransmitter is acetylcholine, abbreviated ACH for short. So the electricity comes down, it activates mitochondria to make synaptic vesicles from the Golgi apparatus, if you remember that, and then it gets what? Gets released into this thing called your synaptic gap or synaptic cleft. Once all these synaptic vesicles that have acetylcholine in it, it moves all the way down, and this is called, goes at the other, this is the postsynaptic area. In the postsynaptic area, that's already where? That's already, your muscle. So now it's the electrical signal coming from this chemical signal. So now acetylcholine will now perpetuate the original electric signal. So it goes electricity, acetylcholine, which is a chemical neurotransmitter, and then back to electricity. And it happens in milliseconds. Okay, so know these parts, know that acetylcholine is a neurotransmitter, and it's specific to skeletal muscle in this case. All right, and it will do what? Signal the release of calcium, and then you can relook at that video regarding muscle contraction. Okay, and this part here on the end is called the motor end plate, or the postsynaptic area, and the space in between the nerve and the muscle is called the synapse or synaptic cleft or synaptic gap. cross-bridge cycling, we saw the video of it. Here's a nice, it's slide 18. Here's a nice representation of it, right? 19, acetylcholinesterase. Well, once the acetylcholine gets used up here in this area, it gets broken down and then recycled back in for the next impulse, and that's acetylcholinesterase right there. Okay, there's also a calcium pump that moves calcium back into the sarcoplasmic reticulum when we don't need it. And then when you don't need your muscle during relaxation, the troponin and tropomyosin on your actin will do what? It will change its shape and then cover up the binding sites. And that's all of this is the exact opposite of contraction. You could also see now here why all the bros in the gym keep on eating tons of creatinine powder or creatine powder, because somehow they think that it will convert their ADP to ATP more efficiently. Again, it's the same fallacy as, oh, I'm going to eat a bunch of vitamins and that should boost up all my coenzyme activity. It doesn't work that way, right? The best way to get creatine is through the diet. That's why when you look at bodybuilders, they use creatine powder as a supplement, but you should see the level of food that they eat, right? That's the main bulk of where they get their creatine from. I keep on making fun of gym bros, but I haven't been to the gym in a little bit, so I should just go now and be a gym bro myself. Aerobic phase, we know that anaerobic doesn't do much, little ATP. The aerobic phase is a lot of ATP, especially in the mitochondria with the electron transport chain making up to 32 ATP. Now, remember when we did that diagram, where does oxygen insert into? It inserts into the aerobic phase, which is in the mitochondria. Now, where did we get all that oxygen from? Of course, it's cellular respiration, but when we're not using it, we store oxygen in muscles in the form of myoglobin. Myo, muscle, globin, protein. So that's the protein that stores oxygen. And we need that for the aerobic phase, which is both the TCA-Krebs cycle and the electron transport chain. Muscle fatigue, because I mentioned that a little earlier, right? You cannot contract muscle forever because everything has to be recycled, and we saw that, and that's why, you know, as hard as you may try, you cannot keep a contracted muscle forever. Now, remember what sparks all of this contraction are electrolytes. Remember, calcium and the balance of it. So when you get a Charlie horse or a muscle cramp, you're most likely dehydrated. And if you're dehydrated, you're also inducing an electrolyte imbalance. And that's how you get Charlie horses. And that's why whoever raised you, right? Maybe grandma told you, well, she always used to tell me, hey, drink a glass of water before you go to bed. I'm like, okay, I just did it. Well, what am I doing? Because think about it. If you sleep 6 hours, you're deep breathing, and you're not having any intake. And your kidneys are constantly making urine, so it's a potential for an electrolyte imbalance. Heat, byproduct, muscles. That's why when you shiver, you produce heat. Remember, the majority of the ATP, right, is released in the form of heat. That's around 60%. Okay. and that's why we shiver. That's why blood is warm. Muscle tone. Now, right now, you're probably sitting in your chair at home, enjoying your day. And what if I took a hammer and I bonked you on the head? If I hit you on the head, what happens to the control center? Do we have any more anything controlling sensory or motor? If you have nothing controlling your motor and or your sensory, because you need to know when you're sitting on a chair, right? Um, is my butt touching the chair? Are my feet touching the floor? Am I stable or am I falling off the chair? Right? And this is muscle tone. It's a continual state of just partial contraction, just enough to keep you upright. But what happens if I bonk you on the head? There is no more signal from your control center, which is your brain, to your efferent pathway. Therefore, what will happen? You will fall to the ground. Okay? So that's what muscle tone is. Next, there are 3 types of contractions, and let's look at 3 stories. The first story is, I went to the gym. I'm going to the gym today, and I picked up a 10-pound weight. I know I haven't worked out in a little bit, but what will I be able to do? I should be able to pick up that weight, and if I can pick up that weight, there is contraction, and the muscle will get shorter. So if the muscle gets shorter, that's called concentric contraction. Now, maybe after a couple of reps, I'm, thinking high and mighty of myself, and now I want to pick up an 80-pound dumbbell. Now, if I have that dumbbell on the floor and I pull on it, it doesn't move, right? What will happen? My muscle will stretch, and but nothing will happen with the movement. The weight is going to still stick to the ground, right? So what happens? I now have my muscle longer. So that's called eccentric contraction. When my muscle gets longer because I can't pick up the weight and the resistance of gravity is too great, that's called eccentric contraction. And last but not least, isometric contraction, nothing moves at all. My muscle didn't get longer because I was trying to pick it up off the ground. And one classic example is, when you kind of stretch in the morning and you get your arms out, but your muscles aren't, when you just cramp yourself up or like tighten yourself up, not cramp, but you tighten yourself up, that's called isometric contraction. You're just tightening yourself up, but there is no movement of there's no, number one, there's no movement. Number two, there is no change in the measurement metrics of the muscle. So in concentric contraction, the muscle is getting shorter. In eccentric contraction, the muscle is getting longer. In both these types of contractions, there'll be movement. But it goes in isometric contraction, there is no movement of the limb, and there is no change in the length of the muscle. So this is good. Know this. Smooth muscle, we kind of already know. Lacks striations, also known as visceral. The sarcoplasmic reticulum isn't that developed to skeletal muscles, because skeletal muscles got to move what? Quick. Smooth muscles, it'll get there when it gets there. Multi-unit smooth, visceral smooth, nice to know, but visceral, lump it all together. And the one thing big about visceral is rhythmicity, just like your cardiac, but it's different. And peristalsis is the motion of how food gets from your mouth to your stomach, and that happens automatically. And visceral muscle is associated with all the hollow organs, which are your gastrointestinal system. Okay. Now, another thing you can add to your skeletal versus smooth muscle is that smooth muscle not only utilizes the neurotransmitter acetylcholine, smooth muscle also uses norepinephrine. Another thing that smooth muscle doesn't have is troponin. Skeletal muscle has troponin and tropomyosin, but smooth muscle has calmodulin. So add these to your chart regarding the differences between skeletal and smooth muscle, because that definitely is going to come out. Cardiac muscle, syncytium, they form a unit, they're rhythmic, they're self-exciting, meaning that they will contract on their own. Okay? Now, what's this refractory period? It's the period of when the muscle has to rest and recharge and get back online. And you cannot have a tetanic contraction. And again, for any of the muscle systems, having tetany or prolonged contraction is not good, and it's you can't hold it forever. You can't hold a contraction or contracted muscle forever. You'll eventually run out of calcium. You'll eventually run out of ATP. And remember, those are the two things that utilizes that causes contraction. I'm trying to speak fancy. I should speak simply. I should follow my own advice. All right. Another thing we have to know about muscles is that in order for you to move, remember I told you guys I bought a taser for my daughter, so me and my daughter had to get tased. Oh. Now, when you see people getting tased, is there any coordination of action? There isn't, because all the muscles are contracting at once. It's the same thing like a seizure. A seizure, there's no coordination of movement, there's no coordination of the signal, therefore there's no movement. So in order for movement to happen, right? Origin insertion, we already went over. In order for my patient here to flex their arm, right? There's going to have to be two sets of muscles. Here you got the bicep, and on the other side, the tricep. In order for flexion to happen, the biceps have to contract. So the biceps here get smaller. And in order for the bicep to get smaller, the tricep behind it has to relax. And that is called this. So in flexion, which is going to decrease the angle of this hinge joint right here, right? The synovial hinge joint right here. We now know the origin is in your shoulder area. So they're here. And it goes, and the insertion, which moves a lot more than the origin, will be, of course, here on your radial bone. So you can see here, I break my radius, can I move my arm? Nope. Break my femur, can I move my arm? Nope. Break my collarbone, can I move my arm? Nope. Break my scapula, can I move my arm? Nope. So biceps will, upon flexion, is the agonist. It's the muscle, it's the main muscle. And it's also called the prime mover, right? Because it is the main muscle that's going to cause flexion of this appendage right here. Now, what's a synergist? A synergist is a set of muscles that help the prime mover, because syn means the same, syn means the same. And the antagonist, that's the muscle that goes in the opposite direction. So in flexion, the bicep has to be contracted. And the tricep, which is the antagonist, agonist, antagonist. So the tricep, that's the antagonist, has to relax, because if it doesn't, you won't be able to move your arm. And that's what happens in a seizure, and that's what also happens in if ever you have the misfortune to be tased. And please don't have the misfortune to be tased. Okay? And the synergist example is, there's a whole bunch of muscles here, but the synergist that I remember is the coracobrachialis, and there's another muscle I can't forget, and they're here. And a synergist, it helps the agonist slash prime mover. So what kind of question could I ask? Upon flexion, which is the agonist? You'll tell me bicep. Which is the prime mover? Bicep. Which is the antagonist? Tricep. Upon flexion, the antagonist tricep will it contract or relax? An antagonist always has to relax, and the agonist has to be the one to contract. Now, can I make it backwards? Because we learned flexion versus extension. So if my patient is extending his arm, therefore the tricep will contract, and then the bicep will relax. And then upon extension, it'll be backwards. The tricep will be the agonist slash prime mover, and the bicep will be the antagonist. Okay, so look over those sample questions that I gave you. I gave a lot of examples of that. Now, this stuff is more for lab, but you could start looking at lab stuff and how to name muscles. Well, there's certain nomenclature or how to name muscles. So they could be named all by location, like frontalis. They could be named by shape. So an orb is a circular muscle. So an orb is like a tennis ball. So orbicularis oculi has to be the round muscle on my patient's eye. The orbicularis oris has to be the round muscle around my patient's mouth. Another type of muscle will be named after what it does. So, for example, the masseter is your main muscle for mastication or chewing. I already mentioned sternocleidomastoid. It could not only location, but what is it attached to? Zygomaticus as well. Zygomaticus is, of course, is your cheek. So what's going to move the muscles or your facial muscles of expression on your cheek, and that will be the zygomaticus. Deltoid is, again, another shape. Pectoralis major. Now, when you have major versus minor muscles are more superficial and they're larger. The minor and the medium muscles are deeper. Another shape is serratus anterior, and it's in the front. And they look like, I call them riblets when I was a kid, but it looks like a serrated knife or like a bread knife. Serrations in a knife, like a saw. So that's why they call it serratus anterior. Rectus abdominis. Rectus means straight. So this guy has little to no body fat because we took all the fat out. And if you have around 5% body fat, your rectus abdominis will be clearly present. You have external oblique, which is on the outside, and they run diagonally. You have your internal obliques, if we removed all of this, and they also run diagonally as well, but they're inside. You have your biceps brachii. Oh, here it is. Your brachialis and brachioradialis. Those are synergist muscles to your biceps brachii. Now, look at the video regarding this stuff here. This is tricky because it looks all the same almost. But remember the sartorius, this one thin strap thigh muscle here. Also know your orientation between anterior and posterior. Okay? These are all good to know as well. Use your medical terminology powers. Rectus, straight, adductor is going to be something that's going to add my limb to midline. Lateralis, it's going to be something that's going to pull or be located on the lateral side. Here's the posterior view. You have another shape here, which is your trapezius. Rear view of your deltoid, and here's your triceps brachii. You have your minor teres major muscles. Major is a little bit bigger. The teres minor is smaller and deeper. You have your infraspinatus. Infra means within. Spinatus, the spine of your scapula. Rhomboid is another shape. Your latissimus dorsi, something that is dorsal or dorsi on your back. Latissimus means wide. So those are your lats. That's what gives that lovely V taper to muscle bodybuilders. And the trapezius here, if you've ever seen a middle linebacker, they don't have any neck. They have a neck, but it's covered with the trapezius muscle that, oh, sometimes in some of these people, it's so big that almost goes down to the level of the deltoid. Gluteus maximus. Max is just like major. It's on the outside. The medius and the minimus are where? Deeper. Adductor magnus is a big muscle where? That's going to help you adduct. So that's got to be on the midline. Because if I want to pull my leg towards midline, where should the muscle be? It should be at midline. Biceps femoris, that means, now biceps and triceps and quadriceps. Every time you see sep, means head. Pathologists, they call, an anatomist, they call like, the main part of the muscle, they call it a head or a body, all right, or a belly. And that's why here, your calf muscle here in the posterior view is called your gastrocnemius. Gastro means stomach or belly, and it's the leg right here. You could see it's connected to your calcaneal tendon, also known as your Achilles tendon. Here's some facial muscles. You have the platysma here, masseter, and you have bones that match up with, muscles that match up with bones. So of course you have your occipital frontalis, so that has to be the occipital to the frontal, and then you have your temporalis, right? Okay. Nice to know. These are the deeper muscles. Again, if we were in a 12-week program, 15-week program, we talk all about these, but again, only the superficial muscles. Okay. Slide 41, a very nice view of deeper structures. And you can see how there are different layers. And the rest here is about movement. We're gonna show that as well. Okay. And all of this stuff, unless it's listed on your anatomage, don't need to know the level of the deeper muscles and the level of minutia. All right, that is chapter 9. I hope you're enjoying your Thanksgiving, and I'll see you when you guys come back next week on Tuesday. Have a good one. Sayonara.